So we've looked at using derivatives to find local maximums using the first derivative test. Okay, so again, taking the derivative setting equals 0, and then plotting a little chart showing that it is negative or positive before and after to show it is a local max or local min. So again, first derivative test. So we are going to look now at determining absolute extreme. Now, let's draw something up here. Let's say we have an endpoint here. And what was that? Let's make out this is it. So that's perfect. Just again, give you an idea. So the important parts about this is one, we do have an endpoint and an endpoint. Right here, about right here, we have a critical value, a critical point. Here we have a critical point. Here we have a critical point. And here we have a critical point. Now, if we're given a graph, we can easily see that right here, absolute max, and right here, absolute minimum. So it's easy enough to identify which ones are absolute max and absolute minimum. Now, with this, the whole point of this drawing is to tell you what are the candidates for your absolute extrema, and that could either be one, your endpoints, or two, your critical values, or critical points. This is a really simple concept here. We're going to do pretty much the same thing we've been doing. You're going to take the derivative, set the derivative equals 0, or again, find where the derivative doesn't exist. And usually, set equal to 0 is where the derivative doesn't exist. That's pretty big issue. But find where the derivative equals 0, and then we are just going to plug the values in to the original function, see what gives us our highest or lowest value. Just have to also include the endpoints. So let's practice this. Here we have our intervals -1/2 and 4. So these are the endpoints. We will include these in our the end of this. But so now that we have the endpoints, we also do need the critical points. So f prime of x is 3x squared minus 6x. We set this equal to 0. We get I can factor 3x out. So 3x and x minus 2. So this tells me my critical points exist when x equals 0 and x equals 2. So we are going to test. Okay, I'm just going to put these in order. You're going to see my lowest value here is -1/2. My next is 0, then 2, and then 4. And we are just going to plug them in. Now we're going to plug them into the original function, not the derivative. So I'm not finding f prime of these, I'm finding f of these. So -1/2 cubed, that is -1/8. -1/2 squared is 1/4 times 3, so that is -3/4 plus 1. If you put that in a calculator, or just know that if you're doing 1 minus 3/4, that's 1/4, and 1/4 minus 1/8 is also 1. So again, on the fractions. 0 is the easiest one. That's just everything becomes 0 except the constant, so that's just 1. Plug in 2. 2 cubed is 8, minus 3 times 2, which is -12, so it gives you -4. So 8 minus 12 plus 1 gives you -3. Now plugging 4. 4 cubed is 64. 3 times 4 squared is 48. Plus 1, that gives you 16 plus 1, or 17. So we can kind of see right here that my absolute max value is at x equals 4, and its value, f of 4, is 17. My absolute minimum value is at x equals -3, and f of 2. Its value is -3. And f of 2 is -3. Now, any questions on that? That's primarily what your work on this section is going to be, is just doing that over and over. Now, we are going to have a lot of questions. AP tests love giving you graphs. Okay. You need to be able to look at a graph and one, know what the graph is of, and this is the graph of f prime, not the graph of f of x. So it tells us a bit of a different story. So, looking at the graph of f prime, you can identify the relative extrema at the x-intercept. So right here, again, if you remember the first derivative test, all right, as my derivative is positive, going from positive to negative, okay, that means my function is increasing and then decreasing. This right here is a max value. Okay, it be relative max value, not a, we don't know about absolute max value, relative max value. Okay, and then going from negative to positive, this is a relative minimum value. Okay. Now, what about the endpoints? That's the question. Endpoints, because we still have to compare them to the endpoints. Now, I cannot tell you what the actual value is. Okay? I can tell you where. Again, can you find the x coordinate of the absolute max and absolute min? And this is not saying what is the absolute max or absolute min, it's saying where is the absolute max. Now, because this is a derivative function, what do we know about the interval from -3 to 1? For the original graph, from -3 to 1, it is increasing. Okay, which means this has a possible absolute min. Okay? Because if I'm increasing everywhere until I get to right here, until I get to 1, okay, and then I start to decrease, okay, then that endpoint is a possible absolute min. This right here, because I'm still after this point, after I have a relative min, because this point is increasing and still after this, this is also a possible absolute max. So which one is your absolute min, absolute max? We are going to look, and again, we will deal with this in a much greater way in chapter 6, okay? To where we can actually verify which one is going to be our absolute max and absolute min. Okay? Because what we're going to do is we are going to look at the area. Okay? So this right here, all this area right here is a positive area. I'm going to do this in red. All this area down here is a negative area and a positive area. So what that shows us is how much it is increasing up to that point. Okay, so let's look at my local max. Okay, my two possible max. So here we have my two possible max. X equals 1 and x equals 4. So what I'm going to do is here I have all this positive area right here, all this positive area right here, and then it decreases. the area goes down, and then the area goes back up. Now, the question is, which one has the greatest area overall? Greatest sum of the area. So for this instance, because all I have up to 1 is positive area, I have no negative area really. But after that, it goes down. I have a negative area. Question is this area enough to make up for that negative area? And just eyeballing it, what do you say? No. Which means my absolute max is at x equals 1. Right. Now let's look at kind of the easier one. Here, I have a possible, so then we have possible absolute min at x equals -3 and 3. Okay. So here, which one do you think is going to be your absolute minimum value? Just looking at the positive and negative area, we want to have at least another area here. So which value is going to get the lowest point after all the area is considered? So the question really is this area enough to cancel out that area? And that is a definite no. This area definitely is not enough to cancel out this area, which means my starting point is my lowest point because I started low, gone up in value, gone a little bit down in value, and then went back up. But this little bit down that I went is not enough to make up for that big amount of area right there. So it means my absolute minimum is at x equals -3. So when dealing with these questions, if they give you the graph of the derivative, right now, all you're looking for is comparing the areas. Okay. Are you starting out higher or lower? Any area that is below the graph. Okay, the area is always, by the way, the area is always considered between the function and the x-axis. That's how you're going to find the area. Any area formed by the graph above the x-axis is positive. Any area formed by the graph and that's below the x-axis. Make a little sense? We will deal much in greater detail on this in chapter 6 because we're in chapter 5. So we are in the actually very last chapter of derivatives. Okay. After this is integration, chapter 6, 7, and 8. Okay. So, and then that'll be the end of the semester. Chapter 6, 7, and 8. Right. So, 5.6. Concavity. Now, what's concavity? The standard quality of being concave. All right. Now we have two types of concavity. You are either concave up, like that, or concave down. Now, the only time you do not have concavity is if you have a horizontal line. So if you have a constant function has no concavity. Okay? But any other function, even, well, you have to be careful with linear functions. Linear functions also don't have concavity, but if you're doing something like absolute value, where you have like two linear functions together, that does have concavity. So even if it is a point like that, that is concave up. Okay, but this or this, no concavity. So concave up. I usually use CU and CD, capital CU, capital CD for concave up and concave down, just because I don't like writing the whole thing out. So let's see what is happening to a function to determine where it is concave up and concave down. So let's see what the derivative is doing. So as of right here, my derivative, I take a tangent line here, and a tangent line here, and here, and here, and here, here. So I'm going from a negative value, negative, 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 to 0, and then positive, 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 positive. So a function is concave up if f prime is changing from negative to positive. Now, that is probably my least favorite way of determining concavity, because that's a lot of work. So, and I mean, if you remember finding your local, we use this also to find your local max and local mins. Okay, there is something we're going to do tomorrow called the second derivative test that will help us. And I think it's a much easier way of finding local max and local mins. So, all right, that should be that. Now, if f is concave up, then f prime is increasing. Yes. So even though, by the way, even though I have a negative value, my negative value is actually going from a large negative value to a slightly smaller until it is a tiny negative value, till it's 0, and then positive. So, and again, it's going from positive to much bigger positives each time. Okay. So my value is actually increasing. If I had a graph of derivative, that would be like a nice linear function, where it's increasing. Okay. Right here is where it would cross the x-axis. So either way, though, the function is increasing. So when this is f, this would be f prime. Now, if it is concave down, then f prime is what? Decreasing. Now, if the derivative is increasing, what is the second derivative? Well, it's just being positive. It's above the x-axis. So where f double prime is greater still means f is concave up. And if f prime is decreasing, that means f double prime is negative or less than 0. So that means f is concave. So here, looking at when we have our points of extremity here f double prime is less than 0. Sorry, greater than 0. Here f double prime is less than 0. F double prime is greater than 0. Here f double prime is less than 0. Now, at each of these points, right here, and it just happens to be on the x-axis, this is not something that happens every time. Okay, each of these points is where the function changes from concave up to concave down. You kind of see where it goes from concave up, and then it is concave down. These points are called points of inflection. And that is where f double prime of x is equal to 0. So what we are going to do is very similar to what we did in finding local max and local mins. Okay, but instead of taking just the first derivative, finding where the first derivative is equal to 0, and then picking points around it, or the intervals around it, picking points in that interval to see where it's positive, negative, we're going to take this second derivative and then do the exact same thing. It's just that the second derivative tells us where the function is concave up and concave down, instead of telling us where I have a local max or local min. So f prime of x, we still have to have that first, which gives us x cubed minus 12x plus 1, and then f double prime of x is equal to 3x squared minus 12. set that equal to 0 to factor out a 3, x squared minus 4 gives us that x equals 0 at plus and minus 2. I'm going to make a small little chart because I have a lot of writing to do after this. Just like yesterday, we have a lot of writing to do. So we have x, and then here, instead of f prime of x, it's f double prime of x. Right? And we have two values, -2 and +2, which we know the second derivative equals 0 there. Then we have the intervals from -infinity up to -2, -2 to 2, and then 2 to infinity. So you're going to plug these values into the second derivative. And again, we can pick any point in these intervals. It could be big, small, makes a difference. Let's say I plug in -3 in here. If I plug in -3 in here, that's going to give me 9 minus 4, which is 5. And 3 times 5 is a positive 15. So that is positive, which means it is concave up. If I plug in 0, because 0 is always just plug in, 0 minus 4 is -4, 3 times -4 is -12, which gives me a negative. That is concave down. Same if I plug in another 3 instead of -3, I'm going to get 5 minus times 3, which is 15. So again, positive, concave up. Okay. Right. So f of x is concave up. At x equals, at on, should say on because these are intervals, on -infinity to -2 and 2 to infinity, because f double prime of x is greater than 0. And f of x is concave down on -2 to 2, because f double prime of x is less than 0. Now, if you are ever asked to find points of inflection and to verify, to give the reason why these are points of inflection, points of inflection at x equals plus or minus 2, because f double prime of x changes signs. So this point of inflection of f at x equals c, if fc is defined 1, like I said, we can only do this if my value is defined. Okay, there are examples of functions where my function does change from concave up to concave down, but I do not have a point of inflection. An easy example of that is something like this. If I have something like 1 divided by x, right there on the left side is concave down. On the right side is concave up. But I do not have a point of inflection because at 0, x does not exist. The function is not exist. Okay. So even though it changes from concave up or concave down to concave up, I do not have a point of inflection. So that's why it says f of c is defined. Okay, in that case, f of c was defined. So he does have to have a value that exists in the domain of the original function, and the second derivative, the signs change at that value. Okay. So in other words, point of inflection is where the graph changes concavity, which is what we just showed. All right. Last page. Now, even though I did show you a function where the f of c did not exist, like at 0, there are some mistakes people make when finding points of inflection. One, assuming that f double prime equals 0 means there must be, really should say is, or really should be must be a point of inflection. Just because the second derivative equals 0 does not mean there is a point of inflection. It is very similar to what we showed yesterday. Just because when f prime equals 0 doesn't mean it's a local max or local min. Okay? A good example of that, go back here, y. This, if I had x cubed, right? So right here, okay, where I can see obviously at x equals 0, my tangent line is 0. Okay? My derivative at x equals 0 would be 0, but that is not a local max or local min. Not guaranteed you have a local max or local min just because the derivative is equal to 0. In fact, it is a point of inflection. So the same reasoning, just because the second derivative is 0 does not mean it must be a point of inflection. That's why you have to do the test to show that the function of the second derivative changes signs before and after that point. The whole reason of the test. All right. Another mistake we'll make is assuming that f prime double prime does not exist means there is no point of inflection. Now, I don't know if I can tell you how important it is to understand the concepts of the graphs. If you're taking the AP test, you are going to be given graphs of either the function, the derivative of the function, or the second derivative of the function, and you need to be able to read them accurately. So let's look at the derivative function. So this derivative function tells me a couple things. One, this right here, my function is positive, so therefore my function is increasing to decreasing, means that this is a local max. Now here, because my function is changing from decreasing to increasing, this is a local min. Right here, even though f double prime would not exist because the derivative is just too sharp, okay, so it does not exist, d on the board, not d. That right here is a point of inflection. Same right here. Point of inflection. And even right here. Point of inflection. So now for the second derivative, if I took the derivative of this function, all right here, my derivative is decreasing everywhere. Okay, so when I wrote increasing and decreasing, that's about the original derivative, or the original function. But since my derivative function is decreasing from -4 to -1, okay, that means my second derivative would be negative. And what happens when my second derivative is negative? That means it is concave down. So I have concave down everywhere. Do this, let's highlight this. So concave down everywhere my graph is decreasing value. So concave down from -4 to -1 and 1 to 2. It is concave up everywhere else. So from -1 to 1, and 2 to 3. And we already talked about the points of inflection, so points of inflection at x equals 1, -1, +1, and 2. Now, if they give you the second group, everywhere it crosses the x-axis, all these right here are points of inflection. So we can go ahead and say points of inflection at x equals -3, 1, and 3. Easy enough. Do be careful, though, because again, it does have to cross. If my graph had done this instead, this would not be a point of inflection. It does have to cross there. Okay? Because the signs do have to change from positive to negative or negative to positive. Signs do have to change. That is the requirement for point of inflection. And the easy part is everywhere above, right? That is concave up. Everywhere below should be that a different color. Below, that is concave down. Easy enough to read. So concave up on from infinity up to -3, and then from 1 to 3. Concave down from -3 to 1, and then 3 to 3. All right, now we got a really fun function. Look at. So, does the line tangent? Remember this question? We asked this question in the last chapter. Okay. Looking at creating the tangent line and then telling me if it's an overestimate or an underestimate by knowing whether it is above or below. Okay, when we talked, we were given in those cases whether the function was concave up or down at those values. Well, now you can define it. You have to show, give the reason, justification, why you can say the line is above or below the graph. Basically, just show at that point the function is concave up or concave down. It is not too terribly difficult if it wasn't for the fact that this is a really fun function to do the derivative and or second derivative. Because not only is this an exponential function, it is product and technically chain rule. Okay. So, what is f prime of x? Well, if we do the product rule, the derivative of the first part, x, is 1 times e to the negative x. All right, plus, that's going to be x times, the derivative of e to the negative x is e to the negative x times a -1. So that gives me 1 e to the negative x minus x e to the negative x. So that means f double prime of x. Now the nice part is this is simple. It's just chain because you do the derivative of e to the negative x of e to the negative x times a -1 because you do the derivative of the exponent. Minus, and I'm going to put a bracket here. Okay, because I'm just going to spread the whole thing. And we do the same product rule again. So again, it's the same product rule, which means I'm going to get a 1 e to the negative x plus x e to the negative x times -1. Now, what we can do, and it really makes no difference because I could simplify this, but it really doesn't make a difference. Because what am I looking for? I'm trying to see if the tangent line is above or below the x, or above, Yeah, below the graph at 1, which basically means if I plug in 1 into the second derivative, you get a positive or a negative number. Doesn't matter what the number is it positive or negative? So let's plug in 1. F double prime at 1. That is going to give me negative e to the negative 1 minus everything, because all these signs become minus, except for that's already minus. So it's become minus e to the negative 1 plus 1e to the negative 1. Okay, well, these two actually cancel out. So I'm left with negative 1 over e. Again, it doesn't matter what the number is, this answer is what? Negative. So f del prime 1 is less than 0, which means it is concave down. And when your function is concave down, your tangent line is above or below. All tangent lines should be what? Below. So the tangent line at x equals 1 will be below graph because f double prime of 1 is less than 0. Yes. Yeah, backwards. Easy to mess up. So that's why you're going to have to really make sure you memorize this. It is, again, less than 0 means concave down. Should make, when I learned this, I had a really goofy teacher, okay? And they always tried to make these little things that made it easier to remember, but it was just so silly. I just hate the teaching, and it was just so silly. When it's negative, okay, negative is sad. So it's concave down. When it's positive, people who are positive are happy. So it's concave up. If I remember that, then I will remember it. So yeah, it is concave, which means it'll be what? It'll be above the graph, not below. Yeah. Yes, it'll be above the graph because f prime 1 is less than 0. All right, so that's it.